Alright, so today we're going to be looking at enveloping algebras, and this is going to be the start of, we're going to be looking at these things for a while, I feel like. And I'm going to say here, there's a few kind of different, similarly titled topics between a few resources that I'm looking at. And I'd rather be thorough than quick, so we're going to cover all of them, so we might end up going back and recovering some of this depending on how samey the topics are. They might be completely different things, I don't know, but yeah, just keep that in mind. We might recover some of this later on. But we'll start off here with the definition. So we're going to let G be a Lie algebra, and this is going to be over a ring K. And then I guess for any associative algebra, just keep in mind the product of an algebra doesn't necessarily have to be associative. It doesn't have to be anything except for bilinear. So for any associative algebra with unit, L is of course the unit and is the algebra and not the unit. And this is also going to be over K. An alpha mapping of G of our Lie algebra G into the associative algebra L is a K-linear algebra no, sorry, it's not an L, it's a K-linear mapping. What does that mean? What would that even mean? So this alpha mapping of G into L is going to be K-linear such that, I guess we're using sigma to denote this alpha mapping, and sigma of the bracket is, it's going to look like a homomorphism, but with the added assumption that the bracket is going to be in its most common form of xy minus yx, and we're just going to write that expansion out directly. And this is our condition for the mapping. And so this is, of course, going to be, we see that is a homomorphism from G into the Lie algebra version of L. Keeping in mind that the definition of the Lie algebra of an algebra is the bracket is the product minus its swapped. If we have another algebra L prime, I'm just going to write as L, which I mean it is an associative algebra with the unit over K. And we also have TAF be a homomorphism, not just a homomorphism, and an injective homomorphism from L to L prime then the composition of TAF with sigma is an alpha mapping of G into L prime. I'm just going to draw myself a little diagram here. So we have G here is our Lie algebra, alpha mapping of G into L. We wrote a sigma, and we have an injective homomorphism from that down to L prime, and this composition is also alpha. So now our goal find a version of L which is universal. And by which this I'm going to assume that they mean for any L prime we can find a map. So I'm guessing we want for any G we want, I'll write this down, for all G exists a L and a sigma such that for all L prime with every L prime exists, and this existence, this first one is going to be unique, being TAF such that TAF composed sigma is an alpha map, which essentially means it's going to be something like that. Maybe not exact, but the essential idea is we can find an L and a sigma which goes into any other L prime and potentially its mapping. I don't know about that. Okay. That brings us to our next definition. I gotta focus on what I'm doing. So, let G be a Lie algebra over a ring K. I'm going to let T be the tensor algebra of G as a K module. So let me quickly unpack this here. So if you don't recall, the tensor algebra consists of the direct sum of every possible tensor product of copies of G. So essentially we have our 0th index is K, our first one is going to be G as a module, next one's going to be G tensor G, third one's going to be G tensor G, and so on. Now of course, for this to be an algebra, we need all of our operations. Addition is just component-wise. and so is scalar multiplication. And our bracket is just going to be the tensor product, which is going to send, not a bracket, it's just our internal product. It's going to be an element of x to the m, g, tensor x, of an element from the n-dimensional tensor of g. And I'm just going to send them to their sum. It's going to send that to the tensor product of the two elements. So if you have like x tensor y tensor x tensor x, is just going to send to x tensor y tensor x tensor x. And this is a map on each pair of components, and you just extend this linearly to the entire space. And it sounds like there's a creature in here with me. One moment. Well, there probably is, but it's not bugging me right now. I don't really care. I'm here to do math here. I'll just write this out. Reminder of the tensor algebra. This probably wasn't the place to do it mid-definition, but we will just section this off here. My drawing pad is not long enough to cover the entire screen, so that's pretty cool. Yeah. Ignore that wedge. So G is of the algebra over K. T is its tensor algebra as a K module. And J, continuing on, J is the two-sided ideal of T, because keep in mind T is not a Lie algebra inherently, so we need to specify the direction of the ideal. In this case it's just two-sided, and this is going to be generated by the tensors of the form x tensor y minus y tensor x minus their bracket, whatever that may be. The associative algebra U, which is equal to T divided by our two-sided ideal, is called the enveloping algebra. Of G. The restriction of the canonical map, I'm just gonna call it pi. I don't know if that's a good symbol to use or not. This is T onto U, which is obviously just sending elements of T to their equivalence class. And the restriction of this to G, because G exists in T directly, right? Is the canonical mapping of G into U. And so it's to spell out exactly what's going on here. In J, we're dividing by J, so essentially we're dividing by the idea in a sense. We're setting that x tensor y minus y tensor x minus the bracket of x and y equals 0, which is equivalent to saying that we want t except we're setting the bracket of x and y equal to x tensor y minus y tensor x. And whatever other conditions we need to have to make that happen, and then otherwise we're just having this thing be as big as possible. And that's what our enveloping algebra is. Let's get that part off screen, please. And we're going to let t positive be the, once again, two-sided ideal of the full tensor algebra T consisting of tensors whose component order 0 is 0. So remember from this the tensor algebra here, the one-dimensional tensor of G, that's just G. The zero-dimensional is the underlying ring, which is going to be K. So we're saying that T plus is just a part of T which does not have this component in the underlying ring. Everything in here is going to be an element of G or the tensor of elements from G. Now, we're going to also let T0, this is going to be K dot 1. Now, what does this mean? K is our ring, and it acts on our Lie algebra by scalar multiplication. And we have that. Does G have a unit? K has a unit. Yeah, this. Oh, no, T has a unit. So this is essentially the identity in T. This is our element 1 in T, which I believe has a 1 in every component. And this is just that element 1, the element gender of it under the scalar multiple of every element in K. Oh, never mind, I didn't read ahead. Don't listen to me. B. So this is the 1 is just 1 in K, so this is the set of elements of order 0, and that is why you don't listen to what I say. And we're going to let u plus and u0 be the canonical images of t positive and t z. That is not a t, that is a u. TO in u. Now, as j is an element of t positive, which essentially means every element in here has a component of order 0 of 0. We can decompose t into the sum of the elements of order 0 and the elements without an term of order 0. And this implies that u is deconstructed the same way. That wouldn't technically be wrong, right? But I want to keep things clean. Thus, u has a unit distinct from 0 and u0 equals k dot 1 inside of u. And so then for all x and u, the component of x in u0 is called the constant term of x. And so we have that the two-sided ideal u plus is elements with constant term 0. Generated by the canonical image of G in U by restriction of by pi of G. Thus, U, the associative algebra, is generated by 1 and pi of G, the image of G in U. As I pointed out before, if x and y are in G, then x tensor y minus y tensor x is congruent to the Lie bracket mod j, and this is occurring inside of T. hence that we get that pi, you know what, I don't want to write pi bar g every time. 0 equals pi bar g. We have, and this is going to make notation easier later on, sigma 0x, sigma 0y, minus vice versa. Is sigma 0 y, so we have sigma 0 is an alpha mapping of G into U. There we go. Alright, so what can we say about things? Let's look here. Go to proposition. We're going to let sigma be an alpha mapping of G into the associative algebra L with unit, of course. Then there exists a unique homomorphism from U to L and this is going to be injective. Injective homomorphism such that sigma equals the composition of TAF with sigma O, which is, as we saw before, where sigma O is, as we saw before, this canonical mapping of G into U. So, how do we know this? Well, we're going to let TAF prime TL be the unique, chose a good time to switch how I was holding my pencil, homomorphism which extends sigma and is injective, essentially. Then what we can do is look at how it acts on our 0 here. So x tensor y, y tensor x minus their bracket from the ideal, which we're dividing out to be 0. Sigma x, sigma y minus sigma y, sigma x minus sigma of their bracket, which is of course going to be 0. This gives us that restriction of t prime to j is 0. It's a 0 mapping. And through the quotient, we can define, using this, a homomorphism T of U into L is going to be injective. Going to put the adjective after, because why not? This is by the quotient. And this is such that sigma is equal to taf composed with sigma 0. And we have that taf is unique by the generators by used generators, as we saw before, 1, and the image of what we're writing now as sigma 0 of the group. Alright, so with this in mind, I can't even draw a square with this thing, man. We're going to let G prime be a second Lie algebra over K with an enveloping algebra of U prime and canonical map of sigma 0 prime, of course, from G prime into U prime. Phi from G to G prime be a homomorphism. Then we have that the composition of sigma O prime, I should probably write out its domain and range just for the sake of making things easier to follow. So sigma 0 prime composed with phi is an alpha mapping map hence there exists a unique homomorphism phi hat from U to U bar, which is an injective homomorphism such that we have another diagram here from G to G prime of phi. This goes down to U as sigma prime. This goes down to U prime as sigma O prime. And this goes this way. A lot of mistakes in this book, I gotta say. That diagram commutes. And this homomorphism, that is phi hat, maps elements of U with constant term 0, which I believe was U plus, right? To elements of U bar, U prime, with constant term 0. Again, constant. And if we have G again, G double prime, another Lie algebra, K with a homomorphism phi prime from G bar in G prime to G double prime. Then, okay, phi prime composed with phi I believe that's what they're going for. Composed with phi hat. And I mean, you can work out the exact diagram for that if you want, but I'm thinking, yeah, it just means that it's just saying that the composition of the maps of their universal enveloping algebras, it commutes with each individual map. Alright, so, well, we got a little bit more time. How much more do we have to cover? Alright, we'll go at least until, we'll check the time again after we get up to this next proposition. We're going to look at the enveloping algebra of a product. Product of Lie algebras, of course. So we're going to let G1 and G2 be Lie algebras over K. And they both have enveloping algebras and canonical mappings as before. We're going to let G be the direct product of G1 and G2. With, of course, universal algebra U and canonical mapping sigma. Then the canonical, a lot of good things are canonical here. Canonical injections of G1 and G2 into G, define canonical homomorphisms of U1 and U2 into U, such that the images, their images commute, because keep in mind the original G1 and G2 are the direct product, and so they're going to commute with each other. And hence, we get an injective homomorphism phi from U1, the tensor product under our algebra K, our ring K of U2 into U. So essentially, the tensor product of the universal algebras is the universal algebra of their product, is what we're saying that. Let's just finish off this section here. Proposition that this phi is an algebra isomorphism. So, proof. The mapping, we're going to call it sigma prime, which sends a pair x1, x2 from G to sigma 1, x1 in the universal algebra times 1 on the other side plus 1 times sigma 2 of x2 is an alpha mapping of G into U1 K tensor with U2 and this is injective such that sigma prime is also equal to the composite of taf with sigma. So for an element x in sigma, element x in G I, sigma I sends that to each side, its respective side, and then taf sends that essentially to sigma. You get what I'm saying, like you can follow it through, I'm guessing. 1 second, let me just double check. And just a reminder that taf is the unique injective homomorphism from U into L it was before. I found exactly how that lines up here, but anyways, you can figure out how taf works from here pretty directly, keeping in mind that sigma is the canonical injection of G into U. And then TAF is just going to be splitting those things as you'd expect. Now, phi composed with TAF composed with sigma, as we see, is phi composed with sigma prime, which is going to be sigma. I guess maybe I should. Okay, yeah, never mind. Sigma, and we similarly have the TAF of phi of sigma prime is equal to TAF composed with sigma, which is just sigma prime, hence that phi composed with TAF and TAF composed with phi are the identity map of U and U1 tensor product of U2 respectively. All right. So essentially, TAF here is just the inverse of our homomorphism phi, sending the tensor of U1 and U2 inside of U. So I guess saying that the tensor of the universal algebras is the universal of the product isn't quite true, because the universal of the product can potentially, looks like, no, never mind, I'm still catching up. Yeah, because we have that everything, this means that our map TAF is just the inverse of phi, and it's also homomorphism, obviously, and so we actually do have that the two things are the same. So this is the end, as since we have an inverse of our homomorphism, it is an isomorphism. And we'll go for one more page just because we got a fair bit of stuff. I want to get it all out in one shot. So U1 tensor K U2 is identified with U under phi. So then the canonical mapping of G, then the canonical mapping of G into U, which we called sigma, I believe. Yes. This is identified, we can identify this over this is identified with the map from x1, x2, this is in G, to sigma 1 x1 tensor 1 plus 1 tensor sigma 2 of x2. And this generalizes to higher tensors. And by that I just mean you get like sigma 1 x1 tensor 1 plus tensor plus 1 tensor sigma 2 x2 tensor 1 plus 1 tensor sigma 3 x3, and analogously for higher dimensions. Everything just kind of unfolds in the way that you would want. And I guess we can call it there for today.